Now that we know what a valid inequality is for the various types of programs we work with, we should ask ourselves, how do we generate valid inequalities? In general, there's two different ways. The first is through some specialized procedure for the problem at hand. The alternative, and the one that we'll discuss here, is a more automatic procedure. We're going to talk about the Chavatal Gomory procedure. In this case, we have a feasible region, X, that's the intersection of some polyhedron with the integer lattice. Our polyhedron is defined by the set of inequalities AX is less than or equal to B. And we write our matrix A as a set of column vectors, A1 through AN. Now that we have this notation at hand, we can go through a three-step process that in some way automatically generates a valid inequality for our feasible region X. The first step is to take all of the column vectors of A, multiply them by the corresponding entries, xj, and then also multiply each of them by a number u. We're going to also take our vector b and multiply it by the same vector u. As long as u is greater than or equal to 0, by multiplying both sides of this inequality by u, we haven't changed anything. We've effectively just multiplied a by a vector u and b by a vector u, and haven't violated any inequalities. The second step is to take all of the entries, u multiplied by aj, and take the floor of them. This is again going to generate a valid inequality because each of these x's is greater than or equal to 0. Since each of these x's is greater than or equal to 0, we're multiplying it by some smaller number, and so this side of our inequality can only get smaller. So the constraint stays the same. Finally, by taking the floor, we've introduced a series of integers. We've multiplied this by our variables, which have to be integers, and so this side of our inequality has to be an integer. Because it's an integer, we can take the floor of the other side. We can take the floor of u times b. This remains a valid inequality. This final inequality, the one appearing in step 3, is the final Chavatal-Gomory inequality that we'd like to generate. And note that to generate it, we've used an automatic procedure. The only thing we had to do was choose some u greater than or equal to 0. After we've chosen the u, everything else is automatic. So now we can talk a little bit about this procedure. The first very surprising fact is that this procedure, if we look over all different values of u, is going to construct all different valid inequalities for the integer program. That is, if we can write a valid inequality for an integer program, then it can be constructed by this procedure. This is a surprising and powerful fact. Unfortunately, in order to construct all of these valid inequalities, we would have to choose many different values of u. There's many different choices of u, and getting a u that's going to give us a good inequality, as opposed to just any inequality, is a hard thing. Also, this procedure can generate a lot of different constraints. Since the freedom to choose u is so flexible, we can generate a lot of different constraints and can't really identify a priori which of these constraints are going to be good and going to be bad. Finally, although we've exhibited the procedure for integer programs, there is a corresponding procedure for mixed integer programs. This corresponding procedure has the same quality, which is the corresponding procedure for MIPS is going to construct all valid inequalities for MIPS.